Hello and welcome back to this series. So in this lab we will be creating or we'll be building a multi-class classifier, an image multi-classification problem with PyTorch. So how we're going to build it? So first of all, this is our data set. So the data set is called animal faces. It's available on Kaggle, so you can go on Kaggle, the link, you'll find the link on the description, and then you can find it here with all the details. So the data set is divided into cat, dog, and wild. Okay, so you have some samples here in the in this page here, and also you have a lot of details also inside this link. You can check it out. I already downloaded the data set from Kaggle the same way we have done last class, and the data set you can find it here, animal classes, and here it is. Okay, now let's start by doing the imports. Okay, so first of all we are going to import Torch, then from Torch import nn, from torch.optim import Adam. Now I'm going to explain why we are importing each of these, but let's finish them first. So from Torch vision import dot transforms, import transforms, and then we are going to write from Torch dot utils dot data import dataset and data loader. We will need the sklearn dot preprocessing import label encoder, import matplotlib.pyplot as plt, and then from pil import image. We're gonna need also the basic things, pandas as pd and numpy as mp, and finally we'll need the os. Okay, now why this is, first of all, this is the main PyTorch library, and then we are importing nn, which is having the layers and the loss function, and then we are importing Adam optimizer, be used in the training, and transforms we are going to use it in pre-processing the images, dataset and data loader to create custom data sets, and the data loader is the object to loop through the batches that divide our dataset to batches. Then from sklearn pre-processing label encoder, we are going to use this in converting our data, our outputs, from strings to integers, integer encoded. And so instead of having cat, dog, wild, we're gonna have 0, 1, 2. And then we are having this one for matplotlib for plotting. Then this one is to read the images. These two are for data pre-processing, and finally the OS to read from the directory. You're gonna know why we need each one later this lab. Okay. Now let's, as we mentioned before, PyTorch doesn't automatically detect the GPU, so you have to tell it to use the GPU. So you have to first declare which device you are going to use. So you're gonna write CUDA, that this device is CUDA, if torch.cuda.is available, else use the CPU. Okay, now let's print device available is device. Now let's see, this is a typo, should be device. Yeah, now let's see what is the available device. So we have a typo here, import from, okay, this is supposed to be from. Okay, and no module named transforms. So I think there is a typo here. Yeah, transforms. Okay, so we are good, and we have another problem here. So from pil import, this is supposed to be image. Okay, these are typo things, so not a big deal. And perfect. So we have CUDA here, the CUDA device, which is the T4 GPU. Okay, great. Now what we need to do, First of all, we need to read all the data here. Okay, so this one contains cat, dog, wild, and this one contains cat, dog, wild, and each one containing its own images. So we're gonna need to split the data set on our own. So the data is split into train and validation. We need train and validation or train and test. Now we're gonna need to split it to train, validation, test. We need this 3 splitting. Okay, so we can do this by reading all the data, everything we have with its corresponding label, and then we split on our own. So we can read all of this inside a pandas data frame. So let's see how we're gonna do this. So image path is equal empty data frame, and labels is equal empty data frame as well. Now for I in os.list there, for what? First we're gonna go into the first layer of the folder. Now this is a matter of layers. You have to think about it as layers. So you first go inside this one, you loop inside AFHQ, and then inside this loop, what you're gonna find? You're gonna find train and validation, which is in this case I. So we are going inside each one, inside the train, what do we have? We have the labels. So we're gonna loop through the label. So for label in os.list directory of f of the same path, but adding to this path I. And then we are going to do the same for image, because each one of these is containing images. So for image in os.list directory or list there, and we are going to have f and the same part, but we will join it with I, comma what, comma label. Okay. Now, what will this print for us? Because I think you may be confused of this syntax. So let me print image, and then I'll do a break here, and then a break here, and then a break here, so that you can, we will just, I just want to show you, I just want to show you the outputs after each layer. So we can have here print I, and then print label, and then print image. Okay, so let's see. If we did this, yeah, this is supposed to be like that. Yes. So do you see that? So we have the first layer, which is AFHQ, and inside AFHQ, it gave us val, which is the validation. And if you continued, so if we didn't break this one, it will give us val and then test, and then train. So let's see. But then this is gonna take some time. No, okay, great. Now it gave us validation, then wild, then this one, then train. So it's looping through that one, okay? I think it's better if we kept the break. You will not get confused. So inside validation, we are going through what we have here. So we are going through the same folder I. So inside validation, what is here? Wild, dog, cat. So it took wild. So I think it's sorting it in some way. But anyway, it took wild because it got into this folder. And then we have image, which is this one. So inside wild, it got that image. So I hope this idea is clear, okay? We want to read each image, okay? Now this is the label, okay? So I want you to remember that this is the label, okay? Okay, great. Let's remove all of this stuff. And we can remove this as well. Okay, now what do we want? We want to append the image path that we got. So for each image, we want to append this image, okay? This complete path of the image, okay? And then we are going to append the label corresponding to it, which is this one, okay? Now, this method may seem complex, okay? If you find any other method, or if you want to use any other method, it's totally up to you. This is on how we read the data, but this is fine, okay? I want to split the data, so I think, in my opinion, that this is a good way. Maybe there is better, but it's fine, okay? This part is not necessarily has to be done like that. It's up to you if you find your own way, okay? Now, after we have read the image path and the list and the labels, so we are going to have a data frame which contains everything is equal to pd.dataFrame of what? Of zip image image underscore path, comma labels, and we are going to have the columns is equal to image underscore path, comma labels. Okay, and then let's see our data frame dot head. Perfect. So now we have the path of the image and its corresponding label. So before also we proceed, let's see the values, the possible values of the labels. So print data underscore df of labels dot unique. It's supposed to be 3. Yes, perfect. Wild dog cat. So we are good to go. Okay. Now let's continue. So what else do we need to do is to split our data. So the purpose of doing this is to split the data. So we need now to split our data set into 3 data frames. A training data frame, a validation data frame, and a test data frame. So let's train equal data underscore df dot sample. Now here, for simplicity, we will not be using the train test split. We will be using that one, okay, the sampling function. So because train test split will give us 4 values. So the x train, y train, x test, y test, and we want the whole data frame. So instead of having train test data, train test split that we did in the last lab, we will do this so that it gives us directly the data frames instead of giving us lists, and then we convert again to data frames. So this is faster. Now train is df.sample of fraction 0.7. What does this mean? So for the training data frame, we want a sample from the main data frame that we have. So this data frame, we want a sample of it, and this sample is 0.7 of the whole data, which means 70% of the whole data. Okay, and then we are going to have the test equal data underscore df dot sample, not dot sample, equal data drop what? Drop the train dot index. Okay, now what did we do here? So we took a 70% amount of our data, of our original data frame, and we called it training. And then these training values are having indices, right? Like these are having indices. So we are going to drop these indices and put them inside a variable called test. Now we split the data because the pending part will be 30%. So which will be the test part. Now we're going to do the next part. It will be the same, but for validation. So validation, we are going to take a sample from the test now, okay? So test.sample of fraction equals 0.5, because we want to split 70%, 15, 15. So 50% of the 30% that we took is 15%, okay? Now test equal the same, equal data underscore df, test dot drop val dot index. Okay, and that's all. Now we can print the shapes so that you can understand now how the data looks like. Dot shape, print val dot shape, and print test dot shape. Okay, perfect. Now we have 70%, 15, 15. Okay, so we are good to go now. We have the data frames splitted. Now what is next? What do we want next? So first of all, let's declare our label encoder. Okay, and then we will have the transform function. Dot compose. Now I'll explain to you what is this, but before we write here, we need to fit the label encoder into our data. So label encoder dot fit on what? On the data underscore df of labels. Now what does this mean? It means that we want our label encoder to give the values for the labels that we have in the data set. So the labels we have is wild, cat, dog. So we want to fit it there so that the label encoder changes automatically. Label encoder will store that automatically. Cat translates to 0, dog translates to 1, and wild translates to 2. Now this could be in any order, not necessarily that order, but with this concept, okay? Now we are going to use the transform. Now what does transform means? What does it do, okay? So it makes all the images having the same properties, okay? Which is the size or the data type or whatever. So we'll start by doing the transforms dot resize. Okay, we want to make all the images are having the same size. Okay, now let's put this inside and brackets. Yeah, and then we are going to have transforms dot to tensor. Okay, sorry, and then we are going to have transforms dot convert image data type into torch dot float. What did we do here? So for each image we read, we will change the size into 128 by 128. We will convert it into tensor instead of normal matrix or numpy matrix. And then we will have it as a float, a torch float type. Okay? Okay, great. Now we didn't read the images yet. We are just declaring the objects that we will be using. Okay? Now let's create the custom dataset. We have a custom dataset, right? So class custom image dataset, which will have dataset, and we are doing the same part we did in the last lab. So we are creating a custom image dataset because we want PyTorch. We mentioned before that PyTorch is like a big ecosystem. So all the objects understand each other perfectly fine. So it's better that we have our data converted into PyTorch syntax or PyTorch dataset. So first we will have this dataset, we call it custom image dataset. It inherits from dataset. So it takes the same functions that we have in the original dataset from PyTorch, and we will just modify these functions. So def init, which is the constructor, we will have itself. It takes self data frame and transform equal none. Okay, by default the transform equal none. So we assume that there is no transform, but there is no transform object, but we will give it a transform, so it's fine. But this is just for having an efficient use. Now self dot data frame equal data frame, and then self dot transform equal transform. Now we are defining the objects inside this class. Self.labels. Yeah, now what will be the labels? Will be torch.tensor. Now torch.tensor of what? This is supposed to be small. Torch of tensor of what? Of label underscore encoder dot transform what? Dot transform data frame of labels, and then we are going to transfer it to device. Now what did we do here? We are creating a torch.tensor. The torch tensor is from what? From the data frame of labels, which is this one. So, but we will use the label encoder to transform them. Transform means that we are going to make them into integers instead of strings. So instead of wild, it will be 0. Instead of cat, it will be 1, and so on. Okay? Now, next is def underscore underscore len. Now, this is a built-in function as well. So we have to use the same syntax. So what does it return? It returns how many rows we have in the data frame, which is self.dataframe.shape of 0. Now the last function is def of get item. This is fully customizable, guys. So that's why PyTorch is very nice, because you can customize everything. You can put your own conditions on how we create this custom data set. You can put like whatever you want and whatever things you want inside in PyTorch easily. So self, it takes self and index, the index of which item you want to get. This is same as well, it's already written inside the dataset class, but we will overwrite it to match our needs. Image path equals self dot data frame dot ilog. So which image path, where is the image path that the user, the index, in which path in the data frame? So we're gonna get it according to ilog function for that specific row, all columns. First column, which is the image path, because the first column is image path. And then we're gonna have label equals self dot labels of idx, and then we are going to have image equal image dot open img underscore path dot convert RGB. Okay, then we will have if self dot transform, which means that the user provided a transform, it's not none, then we are going to apply this transform on the image and move it to device, because we want to move everything into the CUDA device. And then finally we are going to return image comma label. Okay, perfect. Now we are good. So what did we do here? We took the image path according to that specific given index, and we took the label according to that specific index as well. And then we are going to have the image, open the image and load it inside PyTorch. And if we have a transform object, which in our case we have, we are going to do self transform. We will have the transform properties of this, we will make the image into this transform properties, and then we're gonna move it to device and return image label. So perfect, that's all. Now, working fine. Now, let's create the data set for training. Custom image data set, and this one will take data frame equal train, and we're gonna give it the transform equal transform, because we already have a transform. And then we are going to do the same but for validation. So we are going to have val here, and then for test, and we are going to have the test here. And that's all. So let's wait for it. Okay, it didn't take long, so great. Now we have our data set ready. So let me show you one thing. So if we want to use, because PyTorch inside the training will use this syntax by default, but now let me, like, if you want to use it, so data frame dot underscore underscore len, for example, and like that, what we'll have? So the training is this one. And what if we want to use get item? And we are going to use item number 2, for example. So this is the image, and this is the label, which is 0. And we don't know what is 0 till now, but I'm going to show you if you want to know the 0 corresponds to which label. So label encoder dot inverse transform for 0. And let's see what will be the output. It's gonna be cat. So this image corresponds to a cat. So now I hope the idea is clear of the custom data set, and then we can move on. Now, what is next? Next, let's visualize the images. Now this step is optional. You don't have to visualize the images, but this is just to have a look on some random images from your data set. Okay, so let's write n, and this is where we're going to use the matplotlib library. So we're going to have n rows, number of rows. We are going to display it in a grid form of a matrix of 3 by 3, and n columns equal 3. And then we are going to have the create the plot by itself. F comma axarr is equal to plt.subplots, and the subplots are of the size of number of rows comma number of columns. Then we are going into a loop for each row. So for row in range n underscore rows, we are going to have for col in range n underscore cols. So we are looping through each row, then each column. And then we want to read the image. So image equal image dot open. We're gonna need a random image. So data underscore df, random image doesn't matter from training or testing or anything. So random image dot sample, since we want a random image of amount equal 1, n equal 1. We are not using here fraction, we are using n, which is amount. And then of image underscore path. So we're getting a total random value from the image path dot iloc of 0, which means that iloc indicates that we are going to use this item, the index of that item, dot, and convert it to RGB. Okay, great. Now we are going to put our image. So AXRR of row, of that row and that column is dot IMShow image. And we don't want the axis. We don't want to show us this like X axis and Y axis. We don't want this. So you're gonna need to close them. So we're gonna have the same of this one, dot axis off. You're gonna turn it off, and then we are going to have plt.show. Every time you run this, it will display random images, different random images. So let's see. Yeah, there is a path. I think we have copied it wrong or something. Yeah, image path, not path. Okay, so perfect. Now we have the images. If you run it again, different images. If you run it again, different images, and so on. Okay, so great. The images looks good. They are of a good quality, so we can proceed. Okay, so now let's set our hyperparameters. So we're gonna start by setting the learning rate as 1e power minus 4, and we're gonna have the batch size as 16, and also we can set the epochs for 10. You can change these, of course, and that's it. So nothing more we can do here. Then we're gonna have to build the training data loaders, or the data loaders for everything. So data loaders, we discussed this previously. Data loader is used to loop through our data easily. So we're gonna start by the training loop through the data by batches, not just looping. Data loader, we imported this object before. It's gonna take, because data loader takes a PyTorch dataset. So that's why we converted our dataset into a dataset first, into a PyTorch dataset. Now it's taking also batch size equal batch size we created, and then shuffle equal true. So we are going to shuffle the data, change the order of the data because to avoid biasing, and then then we're gonna do the same for val and test. We're gonna have val, and we're gonna have val here, and then we are going to have test, and we are going to have test here as well. And that's it. So we are good, and we have our own data loaders. So what's next? Now, next step is going to be building the model. We're gonna start to write the model class, okay? So like we did in the last lab, let's first start by writing the class, and let's call it network or net, and it inherits from nn.module, okay? So it inherits from the nn class of the nn.module class. The main class is nn module, and we are going to override the functions inside it. We're doing the same that we did in the custom class dataset, okay? Great. So first, of course, let's start with the constructor. Def initialize or init self, and then it's gonna take super dot underscore initialize. Okay, so we are going to use the same constructor that we had for the original class, but we are going to add some things to it. So self.conv1 is equal nn.conv2d. We are going to start adding the layers now. So here, remember, we are just here declaring the layers. We are not doing how the data will flow inside the model. The flow of the data will do it inside the forward function, but now we are in the initialize function or the constructor. Okay, great. So the first convolution layer is going to take 3 channels because it's an RGB images, so 3 channels RGB, and it outputs 32 channels. This number is optional, of course, and the kernel size is 3, and that's all. Okay. Great. Now self.conv2, the second convolution layer, is going to take 32 input channels coming from the first one and output 64, and the kernel size is 3 as well. Self.conv3 is equal to nn.conv2d. It's going to take 64 and outputs 128, and the kernel size is going to be 3 as well. Okay? Okay, perfect. Now, before I continue, let me tell you about the basic convolution neural network structure so you get an idea about that, okay? This is a recap. I assume you already know that, but this is just a quick recap. Okay, now this is from miro.medium/v2, these things, okay? I'll attach these links in the description if you are interested to read more about them. So the convolution starts by having an image, and we do a convolution operation inside the convolution layer and extract multiple channels. So you see this image is 28 by 28 pixels, but 1 channel, because this is grayscale. In our case, it's 3 channels because it's RGB. And so in this case, this number is 1 in this case, and outputs 32, so outputs this number of feature maps. The main purpose of the convolution part is to do edge detection, okay? So if you visualize what is the output of the convolution in terms of images, it outputs an edge detection process. And the more this, like the output channels coming, we call them feature maps or image features or output channels or whatever you want to call it. But the more we have of these, the better, okay? And then we go to max pooling layer, max pooling or average pooling, but in general we go into a pooling layer. The purpose of the pooling layer is that it keeps the number same, okay, but it's reduces the amount of the image, okay? Reduces the size of the image. So it keeps the amount of the features same amount, but reduces the size of them. So we call this dimension reduction, okay? So because it's better for processing and more efficient for processing. And then we go into the next convolution layer to extract more and more features. So we extract more features, and then we go into the pooling layer. Now remember, the pooling layer originally does not reduce the size. However, when you add padding, it reduces the size a little bit. So the purpose of the pooling is to increase feature maps with the same size. The purpose of the convolution purpose is to increase the feature maps, but with the same size, and the pooling layer is to have the same, keep the same amount, but reduce their sizes, okay? And then we do the same process, and then we reach into the flatten layer. What is the flatten layer? The flatten, instead of having matrices, it puts them inside a big vector. And then this big vector goes inside a fully connected multi-layer perceptron, and then a normal, dense, or linear layer, and then the output layer. So we have created already 3 convolution. Now let's create the pooling layer. Self.pooling equal nn.max pooling, max pool 2D, and it's a square 2 by 2. Now I'm going to show you how the pooling and the convolution works in an image shortly, okay? Okay, great. Now what else? Now we only need one pooling layer because pooling doesn't like pooling is working the same through all the images. It doesn't matter the size of the image. It works the same way for all the feature maps. And then we're going to have a self.relu, a relu activation function. This is optional, but it's recommended. Okay, relu. And then we are going to have the flatten layer. Okay, nn.flatten. And then we are going to have self.linear equal nn.linear. Linear here corresponds to that layer, and then the output layer, which is another linear layer. Yeah, now about this is going to be 128 by 16 by 16. Now, don't get shocked of this number, okay? I will explain how we got this number shortly, okay? I will explain it better in the forward function, okay? So no problem about that. Self.output equal nn.linear, another linear layer that is taking 128 from here and outputs len of data underscore df of labels dot unique. It's just getting how many unique labels we have, which will be the number of like cat, dog, wild. This will be 3. So if you change the images data set, it can work immediately. It's dynamically changing, so no need to change again. Now let's go to the forward function. Forward self comma x, and then it's gonna take what? Okay, now how the forward function defines how the data is flowing inside the model, okay? So we need to, like we declare that we have a convolution, a pooling, another convolution, another pooling, but we need to define this path from here till the end. So how we can do that? So first let's start by x equals self.conv1 of x. So first the image goes into the first convolution layer, then x equals self.pooling x, then x equals self.relu x. Okay, now it passed through the first convolution, pooling, and a relu function. So pay attention to this. What is the output here? Before we continue, like what is expected to be an output here? So we started by the image size, which is 128 by 128 by 3 channels, 128 pixels by 128 pixels by 3 channels. Okay, perfect. Now, what is the next part? The next part is expected to be 32 by 128 by 128. Okay, so convolution increases the number of features but does not change the size. Keep this in mind. So the output channels is 32, but the image size is still the same. Okay, now let's move on to the pooling. What is the output of the pooling? Pooling layer does not change the amount of the features, but reduces the size of the feature. So we have here 2 by 2, then 2 by 2, then it's gonna reduce this into divide by 2, and this divide by 2. So it's gonna be 64. Okay. Now up till this point, it's 64 by 64. Relu function does not change anything. Okay, it changes the values inside the matrix, but it doesn't change the sizes or the amount. Now, next part is the next convolution, which is conv2 of x equals self.pooling again, and then x equals self.relu of x. Now, what is the size here? Now, so far we have reached to that size. Now, this size is going to change. The convolution increases the number, but doesn't change the size. So this number is 32, so it's going to be what? 64, you see here. The output going to be 64. And this one does not change. These two does not change. They will change after the pooling. So after the pooling, what is the output? 64 going to be the same, but this one is divide by 2 again. So it's going to be 32. And then we're going to do the same process again. Let's copy paste it for simplicity and change this into conv3. And now this one will be increased because it will increase the number of channels. So it's going to increase to 128, and these two are going to be the same, 32 by 32. Now after the pooling, here we have 128, same amount, But this one divide by 2, so it's going to reach 16 and going to reach 16. And that's it. This number is used here because this is the amount of values inside these matrices that we reach before after the flattened layer. It will make the value like this. It will make, this are the size of the one vector after we make it, after we change from a matrix to a vector. This is the size of that vector, 128 by 16 by 16. And the output is 128. Feel free to change that, no problem. So now x equals self dot flatten of x. We are getting the flatten of x, which will be this output 128 by 16 by 16, and then x equal the first linear layer x, and then x equal self dot output of x, because the output takes 128 and brings us three different outputs or probabilities corresponding to each class. And that's all. Return x. Perfect. Now this is like not it's not difficult. I hope it's clear for you. Okay, we have a syntax error. Yeah, I forgot a comma here. Okay, and that's all. Now let's create our network. So model equal net and move it to device, because we need, don't forget, in PyTorch you need to move everything to the CUDA device or to the GPU device, so that we can have the everything on CUDA. Okay, yeah, this is a typo. Super is supposed to be like that, and perfect. Now we are good. Okay, okay. Now let's see a model summary. Okay, to make sure that we have our calculations correct. So let's use from Torch summary, import summary, and this is corresponding to the model.summary in TensorFlow. But here you must give it the input size. Okay, so input underscore size is equal to 3 by 128 by 128. This is our input size. And let's see the output here. Let's wait for it to load. No. Okay, we have a problem with the shape. Okay, so we must add padding. Okay, why? The purpose of padding is to put another frame inside the image so that we don't lose any features throughout the convolution part. Okay, so it's better that we put a padding of 1 in all the convolution parts. Okay, and run this parts again. Yeah, perfect. Now let's see if our shape calculations are correct. We assumed that the output of the first convolution is 32 by 128 by 128, which is this. Now ignore minus 1. Minus 1 part is going to be replaced by the batch size or the amount of pictures. So ignore this. 32 by 128 by 128. Max pooling doesn't change the amount, but reduces the size by 2. So 64, 64. ReLU doesn't change anything, so it keeps as it is. And then convolution part, 64, because it increases the amount of features and keeps the size the same. Another pooling which keeps the amount of the features the same but reduces the size, and so on, what we explained before. So the output, the input is 32 by 32,768. This is after the flattened layer. And then this is the size of the model, is around 10.75 megabyte. It's not a very small model, but it's fine. 4 million parameters, and great. We are good to go and start the training. But before we start the training, we must define the loss and the optimizer. So criterion equal nn dot cross entropy loss optimizer equal Adam model dot parameters comma LR equal LR. So what are we doing here? We are defining a cross entropy loss. We need the cross entropy because it's a multi-class. If it was a binary, we're going to use the BCE or binary cross entropy. And then we are going to use Adam optimizer, but we are telling Adam optimizer that we want to optimize the parameters of this neural network. Parameters here are also known as weights. So if you want to mention weights, whatever, but it's called here parameters. And we are giving it the learning rate. And that's it. And perfect. So we are good to start the training loop now. So this is the interesting part. So let's start by defining total loss train plot equal empty list. And then total loss validation plot equal another empty list. And I'm going to explain why we are having this, no problem. Train plot equal empty list and total underscore accuracy underscore validation underscore plot equal empty list. Great. Now what's next? Why did we do this first? These lists are to store the epochs, the loss after each epoch of the training and the validation and the accuracy after each epoch of the training and validation, because we want to visualize them at the end and know if there was any overfitting inside the model. Okay, so let's start the training loop for epoch in range epochs. Okay, so we are going to loop by the amount of epochs, and then we are going to define total accuracy train equals 0, total loss train equals 0, total loss validation equals 0, total accuracy validation equals 0. Now okay, first, before we go, okay, why did I do this? Because maybe you are confused now, what is the difference between this and that? So, no problem. The thing is that we are doing this for plotting at the end. So we are having a list that appends each value. So we are appending these values inside those lists after each epoch. And those values, we will be printing them after each epoch. But these lists, we are plotting them at the end to see if there is any overfitting or not. So for inputs, comma, labels in train loader. Okay, so the train loader makes us loop through 8 inputs or whatever. Now, what is the batch size we set? We said the batch size is 16. So it makes us loop through 16 inputs and their labels, 16, 16, 16, and so on until we finish all of them. Okay? Okay. Now, we are going to use optimizer dot zero grad. So we are going to reset our optimizer first, resetting the optimizer, and then we are going to give the model the inputs. So first we are resetting the optimizer. Okay, now this option you can put it at the end or in the beginning, no problem, in the end of the loop or in the beginning. Now we are giving the model the inputs. So the model will give us outputs. These outputs definitely are going to be wrong because the model is not yet trained. So if the outputs are wrong, we need to calculate the loss, which is the error. So we are comparing the model outputs with the original labels. And then we are going to add this error, total loss train plus equal train underscore loss dot item. We are adding this loss into here because this is the loss of the total loss of the whole epoch. So we need to keep adding of each batch until we finish the epochs. Okay, this typo here, outputs. Okay, great. Now, after we calculated the loss, we added the loss.item, so the number of the value inside this training loss. And then we are going to have train underscore loss.backward. We need to do a backward propagation now, dot backward. And then we are going to have the train underscore accuracy is equal to. Now, what is the accuracy? So we need to know what is the accuracy of this batch. Okay. The accuracy is going to be torch.argmax. We need to round it. We need to know which probability of the 3 probabilities we have. Remember, we have 3 outputs. Each output corresponds to 1 probability. like either cat or dog or wild. So we need to get the maximum one. So outputs x is equal 1 is equal to labels. So we need to make them equal to the labels, and this will bring us a list of 16 values. These values are either true or false, and the true ones means that this prediction is true. No problem, I'll print it for you so that you can see these things. .sum.item. So .sum brings for us the how many values are true, and .item brings us the value by itself, a numerical value of how many values are true. Okay, so before we proceed, let me put a break here and another break here and print these values for you so that you can have a clear idea of what we are doing here. So first let's print this, and then we are going to print this whole value. And let's see the output. We didn't finish the training loop yet. I just want to show you how many values are true and false. Yeah, perfect. So now it's the first line printed for us how many values. So the first value is true, is false, true, false, true, false, true. Okay, which means that we have 16 outputs and we have 16 labels. So we are comparing them, which are true and which are false. And .sum.item brings us in total, we have 6 true, 1, 2, 3, 4, 5, 6. So we have in total 6 values are true. So this is the accuracy. 6 values out of what? Out of the whole batch and out of the whole amount of the data for this batch. Okay, so let's clear these prints and clear these breaks, and after that we're gonna do the same as the loss. So total accuracy train is equal to is plus equal train underscore accuracy. So we are going to add the accuracy, and then we are going to tell our optimizer, please take a step and change those weights, because we are in the back propagation now. We are in the back propagation, which means we want to optimize the weights. Great. Now that's it for the training part. Now what else? Like we can go out of this loop now, and we are still in the epoch. We want to do the validation part. So we start with torch.nograd. This is the same way we have done last lab, which means that use the torch, use the model, but without optimization. We are not optimizing the model now. We just want to test it. Okay, we are doing a validation process. We're gonna add another loop. So for inputs, comma labels in val underscore loader. Without this. Okay, and then we will do the same process. Outputs equal model of inputs. Now we are expecting that the model would be somehow better because it's already optimized its weights, but not necessarily. Okay, so but it of course it gets better throughout the training. And then we're gonna have val underscore loss equal the loss function, because we want to calculate the validation loss now. Outputs comma labels, and then we are going to do total underscore loss underscore validation is plus equal val underscore loss dot item. Okay, and then validation accuracy is equal to the same thing we have done here, so we can copy this for simplicity, and then total underscore accuracy underscore validation is plus equal val accuracy. Great. Now we don't need optimizer zero grad, we don't need backward propagation, and we don't need step. We are just testing the model and seeing the result. That's all. Okay? Okay, that's all. Now regarding the next part is inside this loop, we didn't use this. You remember? We didn't use this. Okay? So we're gonna use them now. So we're gonna take this one, total loss train dot append. So what are we going to append? The loss of the training. So which is total loss train append. But let's put round because the loss is going to be a bit high and this is expected, no problem. So let's do round of the total loss train divided by 1000 and comma 4 values only after the decimal point. Okay, and we're gonna take this line, paste, we're gonna have total loss validation, and instead of total loss train, we're gonna have total loss val here. Okay, then we're gonna do the same with the accuracy. So here is the accuracy, we can take it like that, and we can change total accuracy train, and here we are going to take total accuracy training. Now accuracy, we want to display it in percentage, so it's better that we divide it by 100. No, sorry, we want the percentage, so we want how many was true out of the total amount of data. So we can put total accuracy training, we're gonna divide it by the train underscore data set, train underscore data set dot underscore len. You remember the len function, it gives us the amount, the number of images we have inside this training. So total number of images, we are calculating the number of correct ones divided by the total number of images we have inside the training. So divide by that, and then we can take all of this, you see all of this, multiplied by 100 to get a percentage, and round it to 4 as well. And that's it for here. Now we're gonna do the same part for the validation. So total accuracy validation, we're gonna change this into total accuracy validation here, and instead of train data set, we're gonna have val data set, and that's all. Okay, now after that we want to print these values. Okay, so we want to print and see the things like in TensorFlow. So let's print it in a neat and nice way. So print f, and let's put it in 3 quotes, and we can put, for simplicity, and we can put epoch of which one. So epoch of epoch plus 1, because it starts from 0, so we want it in a neat way, out of number of epochs. Okay, and we're gonna have comma train loss, maybe, yeah, train loss. Now you can put this like whatever shape you want, but I'm trying to make it simple and neat, round. Okay, now training loss, we're gonna take the same training loss we have here, total loss train, and we're gonna print it, and then after that we are going to have train accuracy, which is gonna be the total accuracy for training, all of that part, and then we are going to have enter, and the validation loss, so validation loss is going to be this one, total val loss, and the validation accuracy, which is going to be total accuracy validation, that one. This is a printing statement, it's optional at the end, but it's better so that you see the performance of the model. Okay, and that's all. So we can print it now, and we can start the training process now, and let's see. So this step may take some time. Okay, and let's see. Now this part, I hope this is clearly now the difference. I hope this difference is clear between total accuracy train and total loss train, and I mean these values and these lists. Okay, so these lists will be used for plotting, but these values are going to be used for visualization, and going to be used as well to calculate the loss and the accuracy after each epoch and all of that things. Okay, okay, so let's see. Hope everything is going without any errors. The training will take time, so I'm going to see only the first epoch, and then I can stop the video and continue again after it finishes training to avoid wasting time. Okay, so you can leave it, no problem, it will take some time. So I'm having T4 here. If you have better GPU, it may be faster. If you have Collab Pro, of course you can choose different GPUs. Like here you have other ones if you having Collab Pro, but it's not necessarily you go because they are paid. Save, we're not gonna change. Okay, perfect. So everything is going fine. Epoch 1 started by training loss of 33%. 31%, 0.31, 81% of train accuracy, 0.0473, and 87 for the validation stuff. So I'm going to stop the video now and we're going to continue after it finishes training. So the training is done and we are back. So let's continue now. So the training looks good as it reached train accuracy of 99.62%, validation accuracy of 96.32%. And the loss is extremely low, so the model looks very good. So let's test now. We have a testing data. You remember we divide our data set into train validation tests. So let's do the testing. So we start with torch.nograd. Now we explained that before, which means that we are not going to change the model weights. So total underscore loss underscore test equals 0. And then total underscore accuracy underscore test equals 0 as well. And we are going to have 4 inputs, comma labels in test underscore loader. So it's the same way we are doing the validation, but the validation was in a loop, but inside the training loop, but now this is separate. So predictions or outputs or whatever you want to call it is model of inputs. And we are going to calculate the accuracy same way we were doing here. So like that one, we can copy it. It's predictions. And we are going to have also the loss. So we can calculate the loss as well if you want. So this is the part that calculates the loss. I'm gonna change it slightly. So we're gonna have total loss test is, and let's call this as test loss, and it's called predictions, not outputs, and that's all. So great, now we can proceed, and that's it. We can print f of accuracy score is, we can print the accuracy we got. So we're gonna do the same as what we did for the accuracy here. Okay, so here, that's the one. So we're gonna put the round things and calculate the percentage, but instead we're gonna have total accuracy test divide by the test. Now I'm a bit fast here, but because you already know all these steps now. And then we're gonna have also the loss, and loss means the error. So we're gonna have also the loss rounded the same way we were rounding it here. And like that, instead of total loss train, we're gonna have total loss test. And that's it. So let's try to run and see if we have any issues. And let's see, this may take some time depending on the amount of the data. And okay, accuracy is 0. So I think we're calculating the accuracy somehow wrong. Labels.sum.items, so predictions equal labels. So we seem to have some problem, okay, because accuracy doesn't make sense to be 0. How are we calculating the accuracy? So let's print ACC. Okay, let's debug this together. Print ACC is 2. So yeah, there is a problem here. So yeah, accuracy. Okay, we are not adding to the total accuracy test here. Okay, so total accuracy test needs to be like that, ACC. And now it's supposed to give us some valid number. We need to keep adding to accuracy after each batch. So that's the point. Yes, perfect. Now we have the accuracy is around 96%, almost 96%, and the loss is 0.0267. So the model looks really good. Now we can plot the training progress. You remember we had these 4 lists so that we can plot the training progress. So let's plot it. Fig, axs is equal to plt.subplots. We are creating subplots. of number of rows equal 1, number of columns equal 2. Why? Because we want to visualize two plots for training, for accuracy and for loss, and the plots are beside each other, so in 2 columns and in 1 row. And the figure size is, now let's put any size, it doesn't matter, let's put 15 by 5, and let's fix the first plot. So the first plot is axs of 0 dot plot. Now we need to plot the total loss training. Okay, so we're gonna take the total loss train, the list of the total loss train, and we're gonna have a label is equal to training loss. Okay, and we are going to have axs of 0. We're gonna have another plot as well, which is the total loss of the validation, which is that one, total loss validation. And we're gonna put it here, and we're gonna put the label of validation loss, and we need to put a title to make the plot looks good. So dot set title, what's the title we're gonna set? Is training epoch, training and validation loss over epochs. Okay, this is just to make the things looks good, and we're gonna have some labels on the axis. So axis of 0 dot set x label. It's called set x label, I believe. Yeah, set x label, and it's gonna be epochs, and we're gonna have also set y label, which is gonna be, because the x represents the epochs and the y represents the loss. Okay, and then axs dot legend. Okay, great. Now we're gonna do the same but for accuracy. Now this is, but it's gonna be for axis 1. So we're gonna change these to axis 1, and here it's gonna be accuracy, and this accuracy, I'm gonna put this here, training and validation accuracy over epochs, but instead of train loss, it's gonna be train accuracy. So it's gonna be this one, train accuracy, training plot. The first one for the training accuracy, and the second one for the validation of the accuracy validation. Oh, sorry, not here. It's supposed to be here. And yeah, that's it. Now let's do plt.show, and let's see the output. Figure set n underscore rows. Yeah, it's supposed to be n rows only and n columns only without underscores. Okay, no attribute legend. Okay, so we can, yeah, axis of 0 legend. This is to make the things looks neat. Okay, and here gonna put 1. And let's see the output. Perfect, here is the output. So you can see that the output is, we can see if there is an overfitting or not. So you can see between the training and validation, there is some sort of overfitting. Okay, it's, yeah, there's somehow a sort of overfitting now, and here also a very small outfitting in the loss, overfitting. So you can change in the model, you can play with the model, add drop out layers, you can increase the epochs, you can reduce the complexity of the model, and try multiple things and see the results yourself. Now let's go into another interesting part, which is the inference. What if we want to use the model on a separate image from the internet? The model may not be very good, okay, even though we have a high accuracy and low loss, but there is some sort of overfitting, so it's fine if the model didn't predict good. But we want to know if we can predict a model. So I opened this one. I searched for some cat faces. So again, we can take that one if you want, and we can try it. So let's save the image, and let's save it in downloads. And we can go and upload the image here. I'm gonna show you how we can do an inference. So let's take this one here. Okay. Okay, perfect. Now, first thing we need to know is to read the image. Read image. Then second thing is to transform the image into our, using the transform object we created. And then we can give the image model, predict through the model. The model will give us some value, and this value should be inverse transform by the label encoder. Now we can create this inside the function if you want. So def inference, or let's say predict image, maybe predict image, and it takes image. Okay. Okay. Now what should we do? First of all, we need to know how to read the image. So you remember, we read the image through this one. Okay. So we can read the image here. We can give the path of the image. So this one, we can copy the path of it and put it here. Now we have read the image. Now I'm not sure if it can read this format, but let's see. If it doesn't, we can bring another image, no problem. And then we're gonna have to do the transform part. So we can copy it directly, image self.transform, and move it to device. Okay. Image self.transform, we can remove self because we have already the transform object, and move it to device. And we can give it to the model, model.predict, or no, without predict here, model directly image. And let's print the image size as well. Dot shape and model of image, and then return. Okay, let's call this output equal model, and then we can return the output. Let's see. Yeah, here this path, it should be given image underscore path, and we can call this image underscore path, and then we run predict image, and we give the path as that one, and see the output. And we, yeah, so it cannot read this type of images, so no problem, we can get another one. So let's see if it can predict that one, or maybe that one. Okay, so save image and save, and we can go here, upload. This is a JPG image. Yeah, upload, and perfect. Now we got that one, copy path, and we're gonna put it here. Let's see if it can predict that one. Okay, we have a problem with the shape. Okay, so no problem. We got the image as 328 by 128. Now we need one more dimension, which is corresponds to the batch size. Okay, so what if we tried the squeeze function? So it's print image.squeeze. Now I'm trying this with you. So let's see, dot shape. If we squeezed the image, will it fix the issue? No, so it's unsqueeze, I believe. It's one of them. Yeah, so unsqueeze makes it having the batch size thing. So we need to put the unsqueeze part in here. The model expects batches of image. So we need to tell the model that we are only having one image in like the batch contains only one image. So, and that's all. I believe after that it's gonna work. So we are giving it unsqueeze of 0, and then let's tell it to get the output, and perfect. Now we have an output, okay, but we need the maximum one. So it's ranked 0, 1, 2. So we need the maximum. So we're gonna use the same thing we have used here, torch.argmax of the output. Okay, so we're gonna return torch.argmax of the output. So the output is 2. Now what does 2 means? So let's put it here in a nice way. Output equal this one. And what do we want? We want the label encoder I think it was with underscore label encoder dot inverse transform of the output. Let's see. And it predicted for us, okay, we need to take it out from the memory first, so we're gonna use dot item. It expects a list, so we're gonna put like that. Okay, and it gave us wild. It's, even though it's a cat, so no problem. I told you the model is not very good. There is some sort of overfitting, but you can try again and rerun the model again and see. Now, if you see the outputs, okay, so we can print output, and you see here the output, even though it's wild, but you can see that this class is the second highest and this class is the second highest, the lowest. So this is the top, second one, and third one. So it's not a very good model, but this is the way of doing the inference, okay? And I will attach the link of these images, okay? I have also here a GIF that represents the convolution animation, and here for the pooling as well. I will attach these as well in the description if you want to have a look on them. These are not from me, these are from separate links on the internet. I'll put all the links inside the description, and also you'll find the link of the full notebook explained very well inside the description on GitHub. If you have any questions or anything is not clear, feel free to write a comment, and I will reply to this comment as soon as possible. Thank you, and I hope you enjoyed.